Hello, my dear students. I'd like to go over our next bit of material in our study of measurements, and that is conversion factors. I'm going to go over our notes. You can find them in the class stream, but I want to quickly go over them and use my new iPad and a few tricks that I've been shown to cover this section of our material and quickly get you hopefully ready to answer the questions in the accompanying assignment. So I am going to start this discussion by saying that conversion problems are nothing new. The example your book gives and the notes give is, of course, if you're an international traveler and you go different places, perhaps some of you, I know some of our students, at least one of mine from last year, spent the summer in Mexico. And if you travel around the world, you have to work in economies with different types of currency, and there are always values given to the different currencies so that you can convert between, for example, if you were to go to Mexico, dollars and pesos. But we frequently do conversions. For example, if we're traveling or driving, we might be going miles per hour, and you might want to say, if I go 70 miles an hour on my way up to Pine Bluff or to Little Rock, how long will it take me? And you might end up with an answer not in hours, but minutes. For example, it'll take you half an hour, 30 minutes. So you knew there were 60 minutes in an hour. So that's what we're going to be doing. So when you take a measurement and you convert it by multiplying by a conversion factor, when we do that, what we're doing is multiplying by 1, so that our measurement remains the same, but is expressed differently. And by the same, I mean remains equivalent, but becomes expressed differently. And I'll show you a lot of examples here in a minute. So, as this says here, a conversion factor is a ratio of equivalent measurements. And a good example of that would be 60 minutes in an hour. 1 hour is equal to 60 minutes. Or 1 minute is equal to 60 seconds, or 60 seconds is equal to 1 minute. You're expressing two values in a fractional expression where one is over the other, and it doesn't matter. You basically have 1 over 1, and it doesn't matter how you flip the numerator and the denominator, except for when you are trying to, except for the fact that when you're trying to do a conversion, we want to end up with a particular unit in our final answer. And I'll show you what that means real fast. So a classic example here is there's 100 centimeters in a meter, or there's 1 meter in 100 centimeters. And in this case, we have a conversion factor, 100 centimeters per meter. And the smaller number, 1, is associated with the larger unit. And the larger number, 100, is associated with the smaller unit, centimeters being much smaller than meters. So, one of the things in setting up these problems is selecting the proper conversion factor so that when you multiply it, you end up with the units that you want. And of course, since you're multiplying by 1, the actual size of your quantity measured does not change. Here's another example where this is something called a scanning electron micrograph of a surface that shows some individual atoms, but in this case, I must remind you, those are the shadows of individual atoms. But the units, each one of these hash marks here, are a nanometer, or 10 to the minus ninth meters. And if we wanted to do a conversion, to convert from one unit to the other, we would use our conversion factor of 10 to the ninth nanometers per meter, or 1 meter per 10 to the ninth nanometers, the very small nanoscale unit. So, we need to do dimensional analysis as it says, analyze and solve problems and arrive at the units or dimensions that we want. And we're going to do something called dimensional analysis when we do our problem solving. Let's look at an example, and that is, how many seconds are in a workday that lasts exactly 8 hours? Well, if we have 8 hours and we know we want to convert that to seconds, I don't know how many seconds are in an hour, but I do know that there are 60 seconds in a minute and 60 minutes in an hour. So I'm going to have to do my dimensional analysis in several steps. And what I want to do is get rid of my units here, the hours, and move my units to seconds, or S as our abbreviation. So here's the way it's set up. And if I may enlarge this slightly, what we'll have is our original given value of 8 hours, and we'll multiply it by 1 in the form of a conversion factor, 60 minutes in an hour. Notice I put the hour in the denominator. I didn't use 1 hour per 60 minutes. I used 60 minutes per 1 hour so that my hours can cancel out. And then we have the other conversion factor of 1 minute for every 60 seconds. And which do I use? Do I use 60 seconds over 1 minute, or 1 minute over 60 seconds? Well, I have minutes in my numerator, and I want to get rid of that, so I arrange this factor here so that minutes is in the denominator, so those minutes cancel, leaving me with seconds in the numerator. The hours canceled, the minutes canceled, and now my answer will be in seconds. And if you get out your calculator and multiply 60 by 60 by 8, you get 28,800 seconds, and it asks for the number in scientific notation. So, of course, that would be, 2.8824 times 10 to the 4th second. And, of course, we'll leave all the digits in there, because when we're dealing with sig figs and we have these conversion factors, it's at exactly 8 hours, so that's a counting number. That means basically infinite significant figures, and these conversion factors at 60.0000000 minutes per 1.0000000 hours. So all our significant figures, I mean, all of our um, figures in our answer will be significant. And in this case, this particular number has 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 sig figs. We include all our significant figures because all our figures or all of our places as significant figures because these conversion factors were, I don't know what you want to call them, perfect or infinite. So let's move on. And, for example, how many seconds are in exactly a 40-hour work week? In this case, you would have to do the same thing, except instead of starting with 8 hours, you would start with 40 hours, okay? So this technique of dimensional analysis is broadly applicable. And here's another example. You have 50 grams of copper wire, and you want to do an experiment where each experimental protocol, each experimental group, in other words, each student, if everybody's doing the experiment, needs 1.84 grams out of your 50 grams. So I started with 50 grams of copper wire, and I'm using one student needs 1.84 grams of copper. So my grams of copper, grams of Cu, will cancel, and I'll have my number of students in my answer here. And it's going to be, what, a little more than 25. If you get out your calculator and divide the 50 by the 1.84, you will get an answer that is, what, 27.174 students. And, of course, you can't have a fraction of a student, so that leaves you with 27 students with a little bit of copper left over. So that's how you do these experiments, these procedures when you're reporting and discussing experimental data. So when we need to convert from one to another type of unit, and we frequently do it when we're changing ratios and converting between units. We'll have the occasional rare problem where I'm converting between standard measurements and metric measurements, but in general, I don't mess with metric conversions. That's a subject that actually is taught in math classes, I believe in 6th grade, and we will do that process once in a while, but mainly we're going to just stick with metric units. So this is why you need to know your metric prefaces or prefixes. For example, they have 750 decigrams, and we want to know how much that is in grams. And deci, the little d here, stands for 1/10 of a gram. So there's 10 decigrams in a gram. Deci, from the same Latin root as decade, which is, of course, 10 years. So, or the Latin derived word decimate, where 1 in 10 soldiers were killed historically in the origin of the word. So in this example, again, we have 750 decigram, and there's 10 decigrams in a gram, And the question is, how many grams is that equal to? So you'll set up and write down your original value, 750 decigrams. And I'm going to multiply that by my conversion factor, or by 1. And in this case, I have 1 gram equals 10 decigrams. What do I write? I want grams in the top because I want to end up with my units in grams. And my conversion factor would have the decigrams in the denominator. So I multiply that by 1 gram per 10 decigrams, not the other way around. 10 decigrams in the numerator and 1 gram in the denominator. And the way I've written it here, my decigrams cancel, and I will get 750 divided by 10 is 75 grams for my answer. And there it is, written more neatly than I can do it with my Apple Pencil. So that's really about it. You know, there are some other conversions, seconds to milliseconds, gram to micrograms. Okay, how many micrograms in a gram? 1,000,000. How many milliseconds in a second? 1,000. How many grams in a kilogram? 1,000. But here's one, cubic centimeters, which is a length measurement cubed, to liters. And that's a volume measurement, liters. Well, they're both volumes, but remember, when we were introducing our units, we said that a cube of water, 1 centimeter on edge, will have a volume of 1 times 1 times 1, or 1 centimeter times centimeter times centimeter, or 1 cubic centimeter, also known as 1 cc, although we're not really supposed to use that unit anymore. But that volume is also equal to 1 milliliter. And we'll also see that amount of water, at least at 4 degrees, is equal to 1 gram. So that allows for some interesting conversions. So water is, and was originally kind of one of the I don't know, substances used to define and subsequently convert base units. Moving on, one of the things we'll have is long multi-step conversion factors. We'll practice a couple of those in the section review and move on to our next topic of density. So, here's one, 0.0073 centimeters. What is that measurement in micrometers? And remember, for micrometers, our prefix is micro, so we can't call those mm's because those are millimeters or 1,000th of a meters. We use the Greek letter mu for micro. So this is the Greek letter mu. You might also call it mu. We don't entirely know how it was pronounced, but you may have learned of our math fraternity, mu alpha theta, MAT, the beginning of math. So that's the Greek letter mu, and we do know that that's equal to 1 meter is equal to 10 to the 6, 1 million micrometers. And I don't know how many micrometers in a centimeter. Actually, I know, but if I didn't know that, I also know that 1 meter is equal to 10 to the second, because centi is from the Latin for 100, as in century. So 10 to the second or 100 centimeters in a meter. So here's my two conversion factors. So I'll take a two-step approach in doing this conversion because, as I said, I don't know how many micrometers in a centimeter. So here's what I just discussed, my conversion factors. I'll start off with centimeters, and so I'll want centimeters in my denominator, and that'll give me an answer in meters, but that's not what they asked. I wanted micrometers, so in the next conversion factor, I'll want meters in the denominator. And let me show you that problem set up right here. Here's my value, original value in centimeters, and I'm going to multiply that by 1, where 1 meter equals 100 or 10 to the second, or 10 squared centimeters, so my centimeters cancel. And then I'm going to multiply it by 1 again, where my meters are going to cancel out because 10 to the 6 micrometers. There's that funny mu, Greek letter mu, Latin letter mu. Actually, it is Greek, isn't it? That Latin mu is what? Like a U with a tail. And so we have 10 to the 6 or 1 million micrometers in a meter. And my centimeters canceled, and my meters canceled, and I end up with an answer, which is 7.3 times 10 to the minus 2, divided by 100, multiplied by a million, and that's the same as multiplying by, if I divide 10 to the 6 by 10 to the second, of course I subtract exponents, so that would give me 10 to the fourth, but I'm multiplying 10 to the fourth times 10 to the second, so in this case, I add exponents, but this one over here is a negative, so I end up with 10 to the fourth times 10 to the minus 2, ends up with 10 to the 2, so, or let your calculator do it, but you didn't have to use a calculator, because once again, you're always multiplying by 1, and all you had to do was factor out your exponents, and that gives you 7.3 times 10 to the second micrometers. If you are doing this using your TI-84, when you punch these numbers in, please put them in parentheses just to be safe, okay? And then, even this one, you're going to multiply that whole unit by 1 over 10 to the second. You don't, of course, don't have to do that. You can just divide it by, excuse me while I stop this from moving, divide it by 10 to the second, and then take that, or continue multiplying by 10 to the 6, and get your answer when you get to your punching these values in your TI-84. Those parentheses will save you a lot of anguish. So here's an interesting problem. The diameter of the Earth is 1.3 times 10 to the fourth kilometers. You know, what would that be in decimeters? And of course, you know, there are 10 decimeters per kilometer, or, you know, there's 10 decimeters in a meter and 1,000 meters in a kilometer. So you'd have to do a two-step conversion, or you would have to multiply this original value by 1 twice. One where you have 1,000 meters per kilometer, and then one where you have 10 decimeters per meter, unless you knew the original conversion factor between kilometers and decimeters. So, one of the things that confuses people is when we start doing a two-step conversion where we convert 2 units. A good example of that might be where I convert miles per hour in a physics problem to meters per second. And so I have to convert the miles to meters and the hours to seconds. And you just use a number of different conversion factors, canceling out your units each time until you get to the desired units in your answer. So here's one where they're starting with the density of 7.21 grams per cubic centimeter. And they want it, a final answer, in kilograms per cubic meter. So we have to multiply this by conversion factors that convert our grams to kilograms and our cubic centimeters to cubic meters. And just to show you how extensive these conversions can be, I start out with a value that's 7.21 grams per centimeter. And I know that I have 1,000 grams per kilogram, so my grams cancel. And I'm going to end up at this point with kilograms per cubic centimeter. But I don't want cubic centimeters, I want cubic meters. And there are 1,000,000 cubic centimeters per cubic meter. So now my cubic centimeters will cancel, one in the numerator, one in the denominator. And what I end up with is kilograms in the numerator, cubic meters in the denominator. And by multiplying this value, my original value here, twice by 1, or multiplying it by 1 twice by these two conversion factors, I end up with my answer in the desired units. So we're going to just have to do this as we do our data. I don't want to spend too much time on this, but we can derive a lot of information in more practical and usable units when we're doing our experiments. There's some questions at the end. These are good potential test questions. I'll just go over them quickly. I have a value of 1 megagram is equal to 1,000 grams. This megagram here is also known as a metric ton. You'll see it in business and industry because large commodity chemicals are sold in metric tons. Grain and agricultural products are too, when you sell products around the world. And of course, if I wanted to do some conversions, then I would use a factor that gives me this answer. And that would be your answer, 1,000 kilograms per megagram, which is a metric ton. When you do a conversion factor, and for example, we were converting joules to calories, the numerical value may change. It may be by a factor of 10, or in the case of joules, a factor of 4.184. But the actual quantity of our measurement doesn't change. We're just converting it and expressing it in different units. So the quantity does not change, okay? How many micrograms are in 0.0134 grams? One of the problems is this is actually a two-step problem, and that is the first thing you have to do is convert this to scientific notation, 1.34, and I went 1, 2, times 10 to the minus 2 grams, okay? And then multiply that by my conversion factor, 10 to the 6 micrograms per gram. There's my conversion factor. That would be step 2. And if you do that, you would end up with, 10 to the 6 multiplied by 10 to the minus 2. We add, but we're adding a negative 2. So my answer would be 10 to the 4th. So needless to say, that would be your answer, doing it in my head. But if you're ever in doubt, simply multiply your value times your conversion factor, and using parentheses to be safe, in your TI-84, you'll end up with the proper answer. And again, the same thing, converting grams per cubic centimeter to kilograms per cubic meter. In this case, you would use a conversion factor of 1,000 grams per kilogram and 100 centimeters per meter, but it would be, that's per meter, but it's cubed. So it's 100 centimeters per meter times 100 centimeters per meter times 100 centimeters per meter to get my 1,000,000, 100 times 100 times 100 cubic centimeters per meter conversion factor. And in the beginning, you don't have to worry about these. You can look them up, and as you'll see, and a lot of the problems will give you the conversion factor in the problem. So go on to do the section review that's posted today and answer those questions. Ask any questions you have of any problems you have doing it, and we will see you on the next video discussion. And until then,